Hey guys, this is Mrs. Harbin, and this is Pre-Calculus. We are looking at Unit 2.5, Factoring Higher Degree Polynomials. So this chapter we're talking all about polynomial functions, and we're reviewing factoring, so let's look at factoring higher degree polynomials. Our biblical application continues for this unit that God made angles a part of our world. They represent a place where things come together, as well as how things are oriented to each other. Unlike lines, which are infinite, angles show God's use of a finite system of measurement. So we are really getting a handle on graphing and solving for different functions and equations, so that when we put this into the Cartesian plane, we look at different angles, we're able to find precise and finite measurements. Our lesson objective today is this. You, the student, will divide using synthetic division, state and apply the remainder and factor theorems, and factor polynomials with degrees greater than 2. Now, a lot of this should be review. I know that you guys did synthetic division last year, so hopefully this comes back to you very thickly. Synthetic division can be used when dividing by polynomials of the form x minus a. Synthetic division is a shortened version of the algorithm used to do long division of polynomials. So here's your first example. We're dividing 2x to the 5th plus 3x cubed minus 7x squared plus 3x minus 4 by x minus 2. So what we do is we put our number there, 2, and we take our coefficients of all of our variable terms. Because we don't have a fourth term here, an x to the 4th, we do have to put a 0 kind of as a placeholder in there. And our cube term, our squared term, our x to the 1st degree term, and our constant term. And then we follow the rules. We bring down our first number, and we know that 2 times 2 is 4. And we take 2 times 4, which is 8. Add those together, we get 11. 2 times 11 is 22. Add those together, we get 15. 2 times 15 is 30. Add those together, we get 33. And 2 times 33 is 66. So when we finish, we end up with this remainder. Our remainder here is 62. So this polynomial here, this long polynomial, does not factor neatly by x minus 2. And we're going to talk about what that means in the graphing world in just a moment. When we write the reduced polynomial, we bring down our constant term, our x to the 1st term, our x squared term, our x cubed term, and now our x to the 4th term. So we bring down each of those terms in ascending order, with our x term increasing in power with each term. Okay, let's try this one. See if you can do this one on your own. Pause the video, and when you think you have it, come back and check your work. All right, we're going to put the opposite here. Remember we had in the previous one x minus 2, and the opposite of minus 2 went in the box. So here the opposite of positive 1 is what we're dividing by. And we put our coefficients in here. We've got a 5th term. We don't have a 4th and a 3rd term, a squared term, a single x term, and then our constant term. And following the procedures of synthetic division, we get a remainder of 16. And then we bring down our constant term, our x squared term, our x cubed term, and our x to the 4th term. That is our reduced polynomial. Now, let's remind you guys about the remainder theorem. This may sound a little complicated, so let me give you the definition first, and then we'll go and we'll show it with numbers. If a number a is substituted for x in the function p of x, the resulting value, p of a, is equal to the remainder obtained when p of x is divided by a in synthetic division. Let's see what that looks like. So if a number a, we're going to say 3 is our a here, is substituted for x in p of x. So if we substitute 3 in for p of x, and we put 3 cubed plus 2 times 3 squared plus 4, the resulting value will be equal to the remainder obtained when we divide p of x by a. So if we plug in p of 3, whatever we get will be the same thing as if we take this original polynomial and divide it by 3 in synthetic division. Okay, dividing that synthetically, we get a remainder of 49. And when we plug in p of 3, and we evaluate this polynomial with 3 in for every x, we also get 49. So again, the remainder theorem says if a number a, in our case we use 3, is substituted for x in p of x, which we did, we substituted it and we got 49, the resulting value, p of a, which is 49, is equal to the remainder obtained when p of x is divided by x minus a. When we divided p of x by 3, we got a remainder of 49. And when we plugged 3 into p of x, we also got 49. So hopefully now that makes a little bit more sense. And that will work with any number, not just 3, and not just the polynomial in the example. The factor theorem says that if p of x equals 0, if and only if x minus a is a factor of p of x. So when p of x equals 0, there is no remainder. No remainder. Let's try this one. Factor p of x equals x cubed plus 6x squared minus x minus 30. To find the roots of p of x if p of 2 equals 0. Since p of 2 equals 0, that means there's no remainder. So 2 is going to be a nice, neat factor. Let's divide x cubed or x cubed polynomial here by 2. Put in our coefficients from up here, 1, 6, negative 1, and negative 30. And when we divide, we do get a remainder of 0. And our reduced polynomial here is 15 plus 8x plus x squared. And what we divided by right here, x minus 2. So using that factor theorem helped us figure out that x minus 2 is a factor and gave us the reduced polynomial. We could then continue to factor that. I don't know why that disappeared. Using what we know about factoring to get 5 and 3, x plus 5 and x plus 3. So our final factored polynomial is x minus 2. Since we know the remainder of p of 2 is 0, that tells us 2 is a factor. X minus 2, and then x plus 3 and x plus 5 are the 3 factors of x, or the 3 values of x, the 3 zeros of x. That's what I'm trying to say. Remember that when we are factoring to find the zeros of a polynomial, what we're trying to find is everywhere that it crosses the x-axis. So finding those zeros allows us to know when it crosses the x-axis. And we talked about this in the last class, why that might be useful. If p of x has factors with powers, then the power is called the multiplicity of the corresponding 0. Remember, powers are just exponents. So if one of its factors, like x minus 2, is being raised to the second power, it has a multiplicity of 2. That is the multiplicity of the corresponding 0, how many times that 0 occurs. So let's find a polynomial this time with integer coefficients and the following zeros. Here, instead of trying to factor to find what x equals, we're being told what these 3 zeros are, where it's crossing that Cartesian plane. We're going to assume single zeros unless multiplicity is given. So our zeros of our function are negative 1, 5/4, and 3, but 3 has a multiplicity of 2. So first, let's write those as factors. So when negative 1 is a factor, it's x minus negative 1. And when 5/4 is a 0, x minus 5/4. When 3 is a 0, x minus 3. But don't forget, this has a multiplicity of 2. So we're going to stick that 2 up there. So our p of x is equal to x plus 1, x minus 5/4, or 4x minus 5 if you want to get rid of that fraction there, and x minus 3 squared. Now we're going to multiply all of that out. We can FOIL this one here, first outside, inside, last, and get 4x squared, minus 5x plus 4x minus 5. And then we're going to do the same thing here. Something squared just means we multiply it twice. So we're going to multiply x minus 3 twice. And we get x squared minus 3x plus 9. We'll simplify both those and then FOIL again. And when we finally get all that multiplied and distributed, we get 4x to the fourth minus 25x cubed plus 37x squared plus 21x minus 45. Now, I skipped quite a few steps between here and here. So if you're not sure how to multiply these two things or how to simplify, be sure to ask me in class. Today we divided or reviewed division using synthetic division. We stated and applied the remainder and factor theorems, realizing that there's a connection between a remainder and a factor. And we factored polynomials with degrees greater than 2. We also created a polynomial by being given the zeros, being told the zeros and working our way backwards to generate the original polynomial. If you have any questions, be sure you ask me next class.